Lecture 33, the information theory. March 3rd, it's March already. It's unbelievable, but it is. Today we're going to be talking about information measures, and we're going to start on network information theory. So the plan is to spend about half on each. There's a new reading in our book. So, well, in addition to Jung's book, which I think you've been reading now, in particular, the network coding chapter of this book, which I think is very, very good, you should also be reading chapter 15 in our Cover and Thomas book. And those are going to be the primary readings that we're going to be drawing from, but you might also take a look at Elke Mal's book as well. We'll be drawing a bit from that text as well over the next couple of lectures. Office hours are Mondays at 3:30 to 4:30 as always, although I think there might be an interesting talk today. So after class, I'll ask if people want to go to this talk. It's another statistics, computer science like talk, which is relevant to our class. This is the final presentations. We have a deadline tonight, which is March 3rd. We have several more deadlines with regard to your own final presentations, which is one tonight, 11:45 p.m., one Monday, March 10th, and then the final presentations are 2 weeks from today from 2:30 to 4:30 in this room. Okay. But we actually have a lot of assignments now due, and I know I mentioned this a little bit before I started the video, but I might as well say this again. So we have the final project status report due today at 11:45 p.m. We have 3 one-page summaries of paper groups that have been assigned to you due this Friday at 5 p.m. You have next Monday a final project status update 3, which is due next Monday at 11:45 p.m. You need to grade the one-page write-ups that have been written about summarizing your papers. They're going to be assigned to you to grade, and they're due next Tuesday, a week from tomorrow, at 11:45 p.m. Then an additional set of 3 one-page write-ups on an additional set of 3 groups of papers that are assigned to you. They already are assigned to you. They're going to be due a week from Friday, March 14th at 5 p.m. And then the final slides and a 4-page paper are due March 17th at 1 p.m. So basically our class is from 2:30 to 4:30. You need to upload your final 4-page write-up of the papers that you're doing, plus a set of slides to give the talk. I haven't figured out exactly how long the talk is, but I'll tell you the details of that over the next week or so, but plan on like 15 minutes. And that's due 2 weeks from today at 1 p.m. And then the last assignment is that you have March 18th at 11:45 p.m. You have grades for your final set of 3 one-page write-ups for your groups of papers. Don't know others. Okay, any questions about these assignments? This is it. This is the assignments for the next 2 weeks. 2 weeks and 1 day. Make sure it's clear what is due and when it's due. Any questions? Okay. So let's talk a little bit let's do a little review. We've been talking about information measures, and we defined these interesting new sort of non-Shannon-like quantities, like this quantity, which corresponds to the area of the intersection in the Venn diagram. And in some sense, it can be viewed as the information amongst 3 random variables. We also defined this quantity here, which is the area in green, where the center thing is counted twice. And this is called there's a name for this. It's called the total correlation of the 3 random variables. You can generalize that to multiple random variables. This is called the total correlation. It was defined in 1960, in fact. It was a reference I forgot to mention last time. So we have these nice sort of, these 2 measures of information amongst sets of random variables, which can be useful for a number of properties. In particular, they're useful and they come up occasionally in the context of network information theory. And so we can be more general and sort of define a quantity that looks like this, as we talked about last time. So it's the information amongst this M set of groups of random variables, x of g1, x of g2, up to x of gm, given x of f. So it's information amongst these groups given some other group. And as you can imagine, that in this particular case, this corresponds to the information amongst, but there's also a total correlation variant of this as well, which is basically the difference between the sums of the conditional entropies of each group given x of f minus the joint entropy of all other groups given x of f. So that would be the total correlation variance of this. But in this particular case, when we're talking about this measure theoretic, so the sign measure version, we're talking about the first case, when we're really considering the common area within the Venn diagram. And that's a useful quantity. We saw one instance of how it can be used, and in some sense this is like a form of very simple network information theory, and we wanted to ask whether or not it would be good to have sort of two separate views, noisy views of a source X, or two noisy correlated views. And this decision as to which one is better depends on this information amongst three random variables. So which one is better depends on what's true. Which might seem surprising, but maybe it's not, because when you try to answer something generically, you say, well, wait a second, it depends, and then suddenly it makes sense. We also saw other forms of Venn-like diagrams that are applicable. We saw that the Venn diagram instance, when you have four variables, the circular one doesn't really generalize very well. We had this strange kidney bean shaped one, and you can actually come up with very complicated looking pictures when you have 5 variables. But it generally doesn't generalize beyond 3 random variables. But if it's a Markov chain, it does. And if it's a Markov chain, we have these mountain pictures. Because the nice thing about the Markov chain is that the center one, any center variable renders anything to the left and anything to the right independent, which basically means that any center thing renders the left and the right non-intersecting. So x2, when we condition x2, or subtract away x2, then anything less than x2 and anything greater than x2 shouldn't intersect. And so therefore you can perfectly represent the information with mountain pictures. We also saw that none of the information measures that we saw are negative in the case of a Markov chain. Okay, so these information amongst n random variables is never negative. And so we don't have to worry about that either. And we named all these different regions. We have these, A and B and so on and so forth. Okay, so that's supposed to be a different color. Okay, so then we said we saw. I mean, you remember that we saw that the conditional mutual information I of x, y, given z is greater than or equal to 0. And when we expand that out in terms of entropy, it basically corresponds to the submodularity of the entropy function, which is really this. This is this quantity here, where this is really seen as a function of indices of random variables. And we said, okay, well, the entropy also has this property. It has the, empty set is equal to 0 property, and it's the monotonicity property, which basically says uncertainty doesn't. This is the discrete entropy, of course. The entropy is monotone, non-decreasing, because adding random variables can never decrease the uncertainty. And if we consider all possible set functions, functions that apply to subsets of some underlying index set from 1 to n, and all such set functions that satisfy these 3 properties, that's called the cone of Polymatroid functions. And the reason why it's a cone is because when you take conic combinations of any of them, the property is preserved. It's closed under non-negative conic combinations. So it's a cone. And it's a cone in R to the 2 to the n minus 1. Why? Because there's 2 to the n minus 1 values. We're restricted to one value. The empty set value is restricted to be 0. But the other 2 to the n minus 1 dimensions are free. But then we can also consider the set of all discrete entropy functions. And this is a really interesting problem because this inequality, in particular the submodularity inequality, corresponds to exactly what Shannon said was true. This was something that the non-negativity of conditional mutual information really corresponds exactly to the submodularity of the entropy. There's not really any difference. So the non-negativity of conditional mutual information is that a sufficient condition to define all entropy functions? And that was an interesting question. It's like, well, that was not even known. And so the question was, if you consider all the entropy functions and call it gamma h, and all the polymatroid functions, are they the same? We definitely know that this is true, that all entropy functions are these polymatroid functions. These are the polymatroid functions here, in case you're wondering. And let me just make this clear so that, what do we mean by this set of entropy functions? So consider a function f, which maps from 2 to the v to the r, to non-negative real numbers. And any particular subset, so A is a subset of V here. Oops, we don't want to cross it off, we want to highlight it. A is a subset of V, right? And f of A, the evaluation for that index set A, is basically the entropy of that set of random variables indexed by set A. So there's n random variables total. And again, this notation here, we're going to see this a lot today. This index set is the same as the integers from 1 to n. So you should be familiar with that. So you can specify this function by 2 to the n minus 1 values, right? So any entropy function on n random variables can be specified by a vector of length 2 to the n minus 1. Right? There might be a lot of redundancy, obviously, right? Because if the set of random variables are all independent, you can also specify it with only n values. You don't need 2 to the n minus 1. But certainly you could sum together all subsets of the random variables and get a vector of length 2 to the n minus 1. On the other hand, if there's no independence, if all variables are dependent on everything else, then most generally you can specify the entropy function as a vector of 2 to the n minus 1 values. Right? Now consider all possible probability distributions over n random variables. Because what we're changing now is the set of probability distributions. And then we're asking, when we change this set of probability distributions, and we look at this corresponding set of the vectors, the 2 to the n minus 1 length vectors, how general is that vector? Is that vector set? Is that a cone? Is it convex? Is it the same as the polymatroid function? Clearly the polymatroid functions are cone because, like I said, you take conic mixtures, non-negative conic mixtures, and you don't change the polymatroidal assumption. Entropy is not so clear. And so this was a question that was unknown. We talked about this last time, of course, and we answered it. But this is what we mean by this class. Gamma h of n is basically that class of functions which are defined by considering all count of the infinite probability distributions over n discrete random variables. And you could even say that the cardinality of the random variables doesn't matter. You could include, say, okay, well, let's include all possible alphabets. The question is, how general is that class? It seems pretty big, right? It seems like pretty general. And this is where this question really sort of seems very, very fundamental and deep. How general is the class of entropy functions? And it turns out, and this was proved by Jung, the same guy who wrote the book that we're reading in one of his chapters, Zhang and Jung, actually, that they discovered that this was an inequality that was true of the entropic functions. So these are just the generic mutual information, conditional mutual information functions. This is a non-Shannon inequality. It's not the one that's immediately apparent from just saying that the conditional mutual information is non-negative. This doesn't follow from that. In order to get this, you need to search deeper inside of the function, the entropy function. That's what, meaning it's a function of the set of probability distributions. And here's a counterexample. So this is an example of a polymatroid function. So it's a sub-modular monotone non-decreasing function that's not an entropy function. It doesn't satisfy this set of inequalities. And you can get that just by plugging things in. So this is really interesting. So you might say, well, what is this set? What is the set gamma sub n, except for gamma sub n h? What are these strange functions that don't, these strange polymatroid functions that don't include the entropy functions? Can we characterize them? Are they useful? Are they weird? Are they bizarre? Is there certain characterizations of them? Can we recognize them very quickly? And this is still not a fully solved problem. Because as general as entropy seems to be, it's not as general as polymatroid functions, which seems to, in some sense, already capture that which we care about in an information function. It already, it captures the notion of diminishing returns. Conditioning reduces valuation. Information seems to be well represented just by polymatroidality, which is something that Shannon himself realized in the 40s, because he implicitly used the polymatroidality by assuming, by the non-negativity of conditional mutual information again. So that's what that whole bit was about. And I wanted to review that a little bit because I wasn't sure how clear it was last time. But is the idea clear now? What's going on? Okay. So let's do a little bit of notation. We're going to define a couple of other inequalities that are kind of interesting. So, so again, V is a sort of a set, is an index set. It's the integers from 1 to n. And we've already said that, but I'm just reminding everybody. S is maybe some subset, and S complement is, there's a typo there. Is V except for S. Okay. And so we have a set of random variables indexed by set V, and so X of S is essentially just the subset of random variables indexed by set S. And let's say that script C is basically a set of sets. Okay, so each CI is a subset of V. So this is like a set of sets of indices. If you're interested in graphical models, you can think of these C's as being cliques in the graphical model. They need not be max cliques, but they're cliques or something. But they're basically bundles. So what we mean by information inequality, most generally, is the following. So we've got a set of these bundles, right, these C's, and we've got a set of values alpha 1 through alpha k. So let's say we've got k bundles and we've got k values of alpha, and alpha can be any real number. Right? So we're not saying necessarily that alpha is positive or alpha is non-negative. But we're just saying an information inequality takes this form. It's basically something that does this. It says, okay, well, when we take this weighted combination of these entropies for these bundles, it's greater than or equal to 0. So this is a very general thing. So any sort of inequality. So the question is, what people want to study is whether or not we can specify a set of inequalities that fully characterizes the entropy functions. Like we know that the polymatroid inequality, the H of empty set is equal to 0, the monotonicity thing, and the submodularity thing, that's not sufficient to characterize entropy. Whereas, is there a set of inequalities that does this? Like these things, like the mutual information being non-negative. Here's an inequality with a set of bundles. We just take any two bundles that are non-intersecting, and then the entropy of 1 plus the entropy of 2 minus the entropy of the union is going to be non-negative. That's the non-negativity of mutual information. And similarly, we can do conditional mutual information as well. So can we define a set of inequalities that characterize the entropy? We certainly have, we can specify these ones, like the non-negativity of entropy, the non-negativity of conditional entropy, and all these guys are derivable from the above. It turns out that the general Shannon type inequalities, the ones that were sort of used when entropy first came around, take this form, where we're taking non-negative combinations of the conditional and mutual information. So we've got these sets of bundles. I'm using AI, BI, and CI, but we've got a bunch of bundles of random variables, and we're saying that sums of these things are non-negative when alpha is equal to when the alphas are non-negative. And we now know that each term, this basically just corresponds to the submodularity inequality. And we now know that this is not sufficient to characterize, to delineate, to sort of circumscribe very, very precisely just the entropy functions. And the reason why is because we saw that there are these other ones that don't take on that form. Right? Here's one. This is the one that we saw. This is just written in a slightly different form. But it turns out that, is this the only one? Like if we had entropy, the non-negativity of conditional mutual information, and this one, would that give us the entropy function? Well, it turns out that there are others. In fact, here are a whole bunch more of them. And it turns out that this was proven by Mattis, that it turns out that there's an infinite number of them that are needed to describe entropy. So entropy is a really weird beast. When you think about the separation between the polymatroid and the non-polymatroid, this surface is potentially quite complicated. So here are a bunch of inequalities that were shown by Doherty, and then Mattis showed that, in fact, it's not even just these, that there are lots of them. These are all non-Shannon inequalities.
I have a question.
Yep.
So just to be clear, this inequality is has to hold for all entropy functions.
Yes. Every single one of these has to hold for all entropy functions.
And if it's violated, and it can be violated with polymatroid or with some other.
With a polymatroid function, it can be violated, but with entropy functions, it can't.
Okay.
So and we know that polymatroid is bigger than entropy. And the question is, can we characterize the entropy functions by a set of inequalities? And that was what the goal was, is to say, what are the minimal set of inequalities that we can use to say, if you've got this, it's the entropy for some set of random variables. And it turns out that that's not so easy, because there's an unbounded number of these things. So this was the first one to discover. Zhang and Jung discovered it in like 98, 99. They said this one must be true of entropy, but not of polymatroidality. Then these ones were discovered, and then Mattis, I should have had that reference, said actually there's a lot more than just these. And I'm probably pronouncing his name incorrectly. He's a Czech guy. So it's not so simple to come up with a set of linear inequalities on the entropy to characterize the entropy function. So they hope that maybe we could essentially learn to recognize when a particular set function was an entropy function very easily and quickly. It seems far more difficult than what was perhaps originally thought in the 90s. But then this is sort of getting off topic a little bit. If you take my information theory class, my submodularity class, then you're going to say, well, why do you care? Maybe you don't. I mean, you do care, actually, but maybe you don't care. Or maybe you both care and you don't care. That doesn't make any sense. Does that make any sense? These are one of these things, these vehicles that we do to sort of spark interest in your minds, to say, well, how can he be contradicting himself and at the same time teaching us? Because when you contradict yourself, that basically leaves us with just a paradox in our minds. Come next quarter to the submodular class and find out what I'm talking about. But for the purposes of here, of what we're saying here, it basically means that we can't just characterize entropy very simply with linear inequalities. By the way, I should mention that these ones here, these ones were discovered fairly brute forced. It's one thing to show that there exists an infinite number of them. It's another to actually, enumerate them. And these were discovered by these guys, the Doherty. They use computer search algorithm to find them. And these are just 6 of them, 6 more of them. So I don't know. Is this useful? Like, would you go home right now and say, "Oh, I'm going to use equation 33.7 to prove my theorem"? I mean, maybe not. I don't know. There's quite a lot of them. Probably not. Okay, so let's talk a little bit more about some other inequalities, actually, which turn out to be true of entropy, but also more generally polymatroidal functions. And I was debating whether or not to include this in here, but let's say that we've got a set of random variables again indexed by v. And I think the easiest way to visualize this is with a bipartite graph. So let's say on this side we have v, which are a set of, which is the left side of a bipartite graph. So this is v here, and maybe here we have, so this is maybe v1, v2, v3, up to vn. Maybe this is c1, c2, c3, ck. So remember, ci is a subset of v, and vi is a member of v. And there's a set of edges, right, which makes it a bipartite graph. Right? So on and so forth. So the degree of a given vertex, so when we're talking about the degree, we're talking about one particular vertex, like maybe v3 here. The degree is just the count of the number of clusters that contain that vertex v. So it's, when you think of this as a hypergraph, it's basically just the degree. When this is just a regular graph, then each one of the c's on the right-hand side are size 2, and so it's the standard degree of a graph. So everybody got the idea of what degree is? So it's really just counting the edges emanating, counting the edges incident to to each of the v's on the left-hand side of the graph. So there's the minimum degree of a set of set S. So S is a subset of vertices, and R minus S is the minimum of the degrees. And R plus S is the maximum of the degrees. So it's basically just saying, okay, well, here are a bunch of vertices. Which vertex has the fewest number of edges incident to it, versus which vertex has the largest number of edges incident to it. By the way, you're probably recognizing this. Are you recognizing this? This is actually drawn from some of the papers that are going to be on the final presentation, but this just means that you're going to have to talk about stuff I'm not talking about. So I'm only going to talk about a very little bit of these papers. But I warned you when you chose those papers that I was going to be talking a little bit about this. You'll just have to get into the proofs, because I'm not going to prove anything here. So we've got this bipartite graph, which is V, C, and E. E are the set of edges. And I think I already drew that. So this is just defining what that bipartite graph is. Yeah, that's right. So with this sort of formalism, we can actually come up with this very interesting set of inequalities associated with the entropy functions. So we've got a set of random variables, x1 through n. These are discrete random variables. They're jointly distributed according to any distribution. And then C, script C here, is just some set of bundles or some set of clusters. Or it's the right-hand side of a bipartite graph, any bipartite graph. And these are the nodes corresponding to the right-hand side. And assume that every random variable has non-zero degree. Okay, so every random variable is connected to at least one cluster. So we then have this set of inequalities. So the entropy of the whole set has a lower bound and an upper bound, where the upper bound says that we sum over all clusters and we take the entropy of the clusters divided by the minimum degree. And the upper bound, the lower bound, says we take the conditional entropy of the cluster conditioned on the complement of the cluster divided by the maximum degree. So we can special case this to a lot of instances. So this is very interesting in general set of inequalities. These are all still Shannon. They hold for polymatroid functions. They hold for polymatroid functions. And there's also in the paper this notion, which I'm going to talk about very, very briefly, this idea of fractional coverings, fractional packings, and fractional partitions. So here's some examples. So we've got when we say that C is just a set of singletons, then we immediately get this inequality. So the right-hand side, this is our friendly neighborhood independence upper bound. And then the left-hand side is this one that we've mentioned once. It's basically an interesting lower bound on the entropy function, where we take the sum of the singleton entries conditioned on everything else. Okay. If, on the other hand, we take the sets, all sets of n-1 elements, then we get this. So the right-hand side is this. So the entropy is upper bounded by, we can take the sum over all sets of n-1 elements, but divided by n-1. And then the right-hand side, sorry, the lower bound is another form where we're saying the entropy of all, the sum of the entropies of each set of n-1 elements conditioned on the one element that's not in that set of n-1, again divided by n-1, which is this bit over here. This is actually a known inequality. It's Hand's inequality. Hand is a well-known information theorist who's done a lot of interesting stuff in network information theory. We can also define sort of the max overall degree, which is this, and the min overall degree, and we can get another inequality as well. So this is the sum over the individual clusters. And this is actually a fairly trivial consequence of the previous ones because we're just sort of substituting all of the denominators by an upper bound and then pulling it out of the sum. And similarly, we're, I guess on the right-hand side, it's a lower bound, really. We're substituting everything with a lower bound, which makes every one of the terms an upper bound, and then we pull it out of the sum. On the left-hand side, we do this, do the opposite. Okay, so I think, you know what, I think that I'm not going to spend any time on this because I want to get onto network information theory, but there's a little bit of an additional interesting set of inequalities that are based on the idea of a fractional cover and a fractional packing. I think everybody should understand this, but given that we're going to hear a little bit about it for our final presentation, and you're going to be reading these papers, and you're going to be summarizing these papers on Friday. I don't need to go through this that much, except to say that just the whole notion of a fractional covering and a fractional packing is a very interesting way of obtaining inequalities on the entropy function. And then also to stress again that these are still Shannon. These are still true of polymatroid functions. These aren't ones like the ones that we saw a bit earlier. These aren't ones that are true only of the entropy. Okay, so I'm not going to take a break until we get to the network information theory stuff, but I want to talk a little bit about other aggregation functions. So remember lecture 2. Does everybody remember back that far? So lecture 2, we defined E sub k as an event that has some probability. So the probability of E sub k is the probability of P sub k. And the information provided by an event, the Shannon information or the Hartley information, we define it to be the negative log of the probability of the event. Okay. And then the entropy we define to be equal to the average, the aggregation, the linear weighted average of the information. That's the entropy function. And the entropy is a very simple idea. We're just taking the average, the weighted average of the information about the set of events, and that has all these amazing properties. But we could think about taking other forms of aggregation function. Like, for example, let's say that we have this aggregation function phi. This is phi here. And we could then form an aggregation by saying, okay, well, first we take the information of the event here, and then we transform it by phi. Then we take the weighted average, and then the last thing we do is we invert phi to get back the final result. And so phi is an aggregation function, and this does this. So the question is, what aggregation functions might we be interested in? Well, one obvious one is the identity function. The phi of x is equal to x. Right? That gives us back the entropy. Right? But amongst all the aggregation functions, we probably still want this notion of additivity of independent events. So remember, when two events are independent, they multiply. And when two random variables are independent, the probabilities of those events multiply. So if we have these sets of joint events, h and k, the way we can represent them being independent is just writing them as this factor, ph of q times q times k. Now this is the information of event h, this is information of event j, and then this is taking this aggregation function of it, computing the weighted average, because we're sort of adding up the informations here, right, in this bit here, taking the aggregation function, taking the weighted average of it, and then finally inverting the result. And since these events are independent, we probably want additivity, right? Certainly for the identity aggregation function, we have independence of random variables. I mean, basically for this particular function here, for the identity function, what we get back is that, the entropy of x and y is equal to entropy of x plus the entropy of y when x is independent of y. Right, so independent random variables, basically those whose probability is equal to the product, which we have right here. There's the product. Are such that their informations add. The informations are additive. Independent events are additive. So we want to preserve this independence. We want to preserve this additivity of independent events. So the question is, what other aggregation functions might have that property besides the identity function? Yep.
Should there be phi minus 1 on that second term?
Yes, definitely. There should definitely be a phi minus 1. Thank you.
And then that summation is saying that the events are independent.
We're saying that when the probabilities of the events are independent, we want any information measure to be additive in this fashion. In the case when phi is the identity, since we get the entropy, we have that property. The entropy is additive for independent events. If we take some other arbitrary function phi and we apply it here, we're not guaranteed additivity. But what if we insist upon additivity? We say, okay, well, we're only interested in those phis for which additivities hold. Well, we have got one of them, which is the entropy one. The identity one that gives us the entropy. Are there any others? And it turns out that there is another. There's a family of others. Here's the additiveness of entropy. It turns out that there's another family of phis, and it's the only other one. That if we take phi of x is equal to 2 to the 1 minus alpha x, that one also leads to additive events, strangely enough. We have to take alpha not equal to 1. Otherwise it doesn't make sense. So what we get then, interestingly enough, once we do this and we do a bit of algebra, we get what's called the Rényi entropy of a set of probability distributions. And for alpha greater than 0, this is the form of the Rényi entropy. It's basically 1 over 1 minus alpha times the log of the sum of the exponentiated probabilities. This one preserves additivity. So like independent events is still
And you
additive.
said this is the only Are all functions that preserve additivity are in this one?
It's either the identity or of this form. I mean, there are others that don't preserve additivity, but we care about additivity. And the NA entropy is one. We have a certain set of properties of the NA entropy. We're not going to have a chance to go into a lot of details about it, but this is another form of information function on probability distributions. It's monotonically decreasing with increasing alpha. And we have these bounds that when alpha is equal to 0, it's equal to log of n. And when alpha is equal to infinity, when alpha approaches infinity, it's negative log of the maximum probability. And interestingly enough, also if we take the limit as alpha goes to 1, we get back the regular entropy. So in some sense it generalizes. It's not easy to see this because when you plug alpha is equal to 1 in here, you just get back 2 to the 0. But when you take the limit inside of this expression, you get back the entropy, which it can be shown.
Can you mention any applications of this? Is this sort of entropy more suitable for certain types of distributions on different types of data? Or
it might be. This is, from my understanding, there haven't been a very large set of applications of the Rényi entropy, or certainly practical ones. I think it's primarily been done from mostly a mathematical perspective to try to study its properties. People have plotted them, and you might say, oh, the entropy looks like this, but the Rényi entropy looks like this. It's more square or something, or maybe it's more like this or something. So it has different properties. Like maybe there might be an application where you want to give maximum entropy before it gets to be equal to uniform. You want to sort of extend the range when the entropy is maximum. You're perfectly happy to say that it doesn't have to be uniform to be most uncertain. A lot of these are still concave, but there hasn't been sort of this universal. There's Kimchin's theorem, remember, that said that in any one of these ones that satisfy these three properties that we proved several times now, has to be the entropy, meaning the Shannon entropy with a log function. But the point is that this is not everything. So this is still, I would say, every few years there's another paper on this. And it's been happening since about 1970. There hasn't become yet a universal application of this. But this might be useful. It's certainly differentiable. I think there may be a utility in machine learning at some point. I don't know. I don't want to mention it because it's not the case necessarily that regular Shannon entropy is the end-all, be-all of the entropies. And in fact, there are lots of others, other forms of entropy. There's Droxys, there's the quadratic entropy, there's the R-norm entropy, there's the Havra-Shavrat, and I'm not even sure, I'm not pronouncing those correctly. Sharvat, I think it is. They all have slightly different definitions, and then different shapes, different forms. And in order to see whether or not they would be useful for you, you'd have to study the properties. And people have studied them mathematically, but there hasn't yet been a killer app for any of them, as far as I know. Okay, so that's all I'm going to say about these entropies. You should be aware of them. The Rényi is by far the most famous of the alternatives. So you should at least know the definition of the Rényi entropy and know that there are some other ones as well. Because you do occasionally see these in the literature. Okay, this is a perfect time to take a break. So let's take a break now, and I'll see you after the break. If there are no questions. Are there other questions? Okay, welcome to the second half, and this is going to be the topic for the rest of the quarter, which is network information theory, or as it's known in the in circles, NIT, which is not true, I just made that up. So basically, we've had this model of communication that we've sort of used throughout the entire two-quarter sequence so far, implicitly and explicitly, which is that there's one sender and one receiver. So we're at point A, and we want to send something over to point B. Right? And that's a very nice thing that sort of corresponds to many, many scenarios, for example, to radio broadcasts or to point-to-point communication types of things, and so on and so forth. And we quantified information from that perspective. We've got this notion called entropy, and we've studied communication limits under this particular notion of information. We have the notion of a rate. We have the notion of error-free communication, that we can't communicate above a certain rate without there being severe consequences. But if we communicate below the rate, then we can actually communicate with vanishingly small probability of error if we're willing to allow for the block lengths to be as long as we want. Is that right? Yes. So when the rate is greater than the capacity, there's no hope to communicate with a small amount of error. So we also realized, and this was an very important realization and not even obvious at the time, which was that source coding and channel coding could be separated. That we could take a source, compress it down to its entropy, and then we could communicate perfectly, with a caveat on what perfectly means, that source as long as the entropy is less than the capacity of the channel. Right? If the block length is big enough. And here's our model. And you can think of this as a very simple network, right? It's a very simple network that's from point to point, right? So here's one point here, and there's another point over there, and we just communicate from point to point. Very simple network communication. General network information theory is much more apropos to modern networks, where we've got multiple simultaneous senders and receivers that are simultaneously trying to communicate to each other. Sometimes they're trying to communicate similar information. Sometimes they have the same parts of the same information, different parts of the same information. Sometimes these senders are correlated. Sometimes these senders aren't correlated. Sometimes the senders and the receivers interfere with each other destructively, where one sender might be seen as noise to another sender. In other cases, maybe that's not the case. But we can still ask the same kinds of questions, which are, what's possible? When you've got a given network or a particular type of network, what is achievable from the perspective of, does there exist? This is, again, just asking existence proof questions. For a given set of rates, which must exist, there's not any one rate now because every sender has their own rate. For a given set of rates, does there exist a set of network codes where everybody codes according to some rules which might allow cooperation or which might not allow cooperation? Does there exist a set of rates that are achievable in the same sense, that you can get vanishingly small probability of error for everybody, or at least some subset of everybody? So it's still a very active research area. I mean, in the past 10 years, there's been a lot of fundamentally new work on network information theory, some of which we will discuss in this class. And here's a very general case first. So we've got a network. In this particular network, it's a clique, right? So at every point, which consists of each one of these vertices, you've got a sender, X, and a receiver, Y. And every sender wants to communicate something to every receiver. And every sender might send a message directly to the receiver, which might be a valid way. Or a sender might send a message indirectly to a receiver. Like, for example, let's say that X1 wants to send to X4 and XM, so it first sends to this guy and then sends to this guy and this guy, in addition to sending this one and this one, because maybe these other links are bottlenecks. So maybe you can increase the rate of X1's messages to this guy and this guy by going through this path and this path simultaneously. So you need to somehow jointly code. Or alternatively, maybe everybody wants to send to X3. So X3 is a receiver, so everybody's trying to send to this guy. And maybe there's some shared channel that X3 uses, and so there's this bottleneck. And so how do these things cooperate or communicate? And the question is, do the senders get to coordinate? If X1 and XM could communicate to each other to figure out how they should cooperate with each other, that's a very different set of rates than what would happen if x1 and xm can't communicate, because maybe x1 and xm are very far away from each other, and just from them communicating to each other is costly. And so you want x1 and xm to communicate, to be able to send to x3 without having to communicate to each other. So you can imagine that this generic scenario can involve many, many different interesting possible instances of what we could call network information theory. Now, this is not a solved problem. There's no universal generic for this most general case set of, say, achievable rate regions, which can describe all cases. And what has happened over the past 20, 30 years, maybe longer, is that people have started studying very, very special cases, like the multi-axis channel on the map, which we're going to start studying today, the Schlepping-Wolf theorem, and a bunch of other things. These are all basically special instances of this picture for which we can get some knowledge about the achievable region. Now, the region is no longer just a point. It's no longer to say that there's a capacity, but we're in n-dimensional space, and we can have points within this n-dimensional space, and each point in this n-dimensional space corresponds to a set of rates. And you can either say, yes, this set of rates is achievable, or no, it's not achievable. So you still partition this space into achievable versus non-achievable regions. But the question is, how do we characterize this n-dimensional space? Can we characterize the boundaries within which we know that if we're in the achievable region, there exists a set of codes that achieves vanishingly small probability of error for everybody? Or maybe even, like I said, you don't need it to be for everybody. It can be for some set of people, some set of communicators. And then if you're outside of this achievable region, you're guaranteed that you can't communicate. So that's the idea of network information theory. So it's a very standard, and very important generalization. So the other thing to remember, again, is that the senders can potentially, there are models where the senders may be allowed to communicate. So the senders need not be independent. If the senders can't communicate, then it's an assumption of independence. And there are instances where you make that assumption because it's practical. Independent sources means that there's no cooperation. But on the other hand, it might mean that they stamp on each other's foot. Like one guy's signal is another guy's noise. Have you ever been at a party and you're both trying to talk to the same person and you're both talking simultaneously? If that person is only listening to one of you, then the other person talking to that person is noise for both of you, right? So somehow you have to, and now imagine trying to do that independently, whereas the two speakers can't see each other, don't know about each other. How would you still be able to communicate to that person at a party? That would be a very challenging problem at a party. So somehow those are the kinds of things you want to do. So like I said, the goal in some sense is to compute the achievable region of capacity. So like you have some probability distribution, which is some generic, in this most general case, it's the generic joint probability distribution over n random variables. And we have the capacity function. And the capacity function is really a vector value function, right? It's basically not saying, it's saying under this joint distribution, this is what's what's possible, or maybe it's not possible. So it's the capacity. In some sense, it's really, I guess I shouldn't call this capacity, I should call this like a rate. This is like a set of rates. This is the rate at which these things can communicate without error. So let's make this a little bit more general and say, okay, so we've got V's again going to be our set of sources. So we've got M of them. And what we want is a capacity function that gives constraints on the rate limits for communicating sources of S. So basically, we, like in the case of regular point-to-point communication, we say, okay, the rate has to be less than the capacity. It's a scalar case. Okay. But now we might say, okay, well, this rate has to be less than, so the rate of sender 1 has to be less than some amount. The rate of sender 2 has to be less than some other amount. And some aspect of both of these rates has to be less than some other third amount. And so for every possible subset of senders, we might have a constraint on the joint rates of all of those senders. And so therefore the capacity function is really a subset function that maps from all subsets of senders to the capacity limit of those rates. And so we might actually have an achievable polyhedral region where it says, okay, well, the sums of all rates for any given S, for any given set of senders, the sums of all rates can't exceed the capacity of that set of senders without, again, there being guaranteed error. So if n is equal to 1, we've got the same situation we're familiar with. It's just a capacity. When m is greater than 1, we've got something a lot more interesting. And you can think of this based on there being some underlying joint network channel, which basically says, and it's modeled by a conditional probability distribution. Most generally, it's saying, okay, well, for any given x1 through xm, we've got this particular noise profile jointly. So this allows for there to be interference. If xm is one particular thing, if you're trying to communicate at a particular rate, you might interfere with some other sender. This allows there to be interference. Yep.
Just to make sure I understand, for 33.23, what are the dimensions of that polyhedral region? Like if n equals 2, you have 4 dimensions?
If m is equal to 2, you have 2 dimensions.
Okay.
And it's basically saying, I'll have some pictures of this. And it's basically saying that you have a constraint on the singleton rates, and you also have a constraint on the joint rates, both, which may not be the same necessarily. Oh, when you see a picture, we'll actually see lots of nice pictures over the next few days. Right, so like I said, there are special cases of this generic situation. The kind of stuff that we analyze are these special cases. We can't analyze this most general case yet. And in fact, some of them are quite soft. But other instances, and in fact many real-world cases, are not solved. And it's only possible to obtain bounds on the achievable region. Like maybe we have an inner bound in the achievable region or an outer bound in the achievable region. So that maybe we know that there exists a code once we're at a particular rate vector. But that we don't know if we can actually improve this rate. We don't know if there exists a sequence of code for which the rate improves. The other thing to mention, of course, is that right now the nodes themselves may, like we went back to this picture here, the nodes might be active. Like if we're trying to send from 1 to 3 via 2, 2 might be doing some recoding, right? Because node 2 might be trying to communicate, like m might be trying to send to 3 via 2 as well. And so node 2 might actually need to do some recoding, some decompression, recoding for that particular channel in order to achieve a given rate. Right, so we have to also start thinking in some sense about the nodes themselves being active, being computational units. They're not just passive things that sort of pass by bits or concatenate bit strings together. They might need to recode those bit strings. And that makes it very, very interesting. It's at this point here. Right, and like I said, these active nodes might be the difference between being able to do it or being not be able to do it. If everything's passive, you might have a very different set of rate profiles than when things are active. So, okay. So first of all, let's just define the notion of typicality in this more general setting, which is going to allow us to essentially express a lot of these things. Now this notion of typicality was done in the very early days when people said, okay, well let's just generalize Shannon's notion of typicality to sort of be able to see the degree to which we can express achievable regions within the network. And that took us pretty far, but not as far as we'd like to go. But let's first of all define it. So we have m random variables, and we're going to use the superscript to index which random variable it is. Okay. So here's the superscript. And again, we have m total random variables, and S is some subset of indices. And so we can, for example, talk about like x of S, which would be a subset of random variables. And the reason for using the superscript to index which random variables it is because we're going to be talking about blocks of length n of these samples of random variables. Just like when we have one random variable, we need to block code length n samples in order to achieve a given rate, with vanishingly small probability of error. We have to do the same thing here, except that right now we're coding blocks of length n of vectors of random variables. And so we have this notation. Right, so here's our matrix, really. We've got a block of length n of m random variables. Okay. So you can think of n as like time, maybe. M is the vector. And then for any given subset of random variables, we can talk about a block of length n of that subset S. One thing to note is that we're taking independent samples of these vectors. We're not saying that the random variables, that the m random variables are independent, but these samples are independent samples. So it's still the case that there's not, we're not saying, just like what we saw before, we're not saying that there's a time dependence. But we're talking about vector value random variables, for which there could be dependence. And so therefore, when we say what's the probability of this set of random variables, we take the product over each time step. So that's the generalization. Here's an example. When S is just two indices, JL, then the probability of this block of length n of pairs of random variables is just basically this product here. It's a silly example, but there it is nonetheless. We have by the weak law of large numbers that when we take the negative log of the probability divided by n, that converges to the entropy. It converges to the entropy of the set S of random variables. And so we actually have 2 to the m possible subsets, to the n possible entropies. We might actually be able to compute in this fashion. And we also have 2 to the m possible typical sets. And so you remember the notion of jointly typicality, right? So joint typicality said, okay, well, you have to be singularly typical, singularly x typical, singularly y typical, and you also need to be xy typical. So we had 3 notions of what were 3 constraints on what was necessary in order for this pair to be typical. But now we've got m random variables, and so we have 2 to the m possible constraints on what's necessary in order to be jointly m typical. And so let's just define for all subsets of V, let's call this is going to be one particular constraint for a particular S. And so this is all sequences that are epsilon close in this sense, meaning that the average probability is average log probability is close to the entropy, epsilon close to the entropy. And this is also true, I guess let me point this out, that this is true for all subsets of S. So when S was of size 2, that corresponds to the set 2, and then also the singletons 1 and 2. I think I have an example of that. Right, let me just mention this. I guess when S is the empty set, it's vacuous. That should be clear. So when there's no random variables, there's no constraint. So again, it's really like 2 to the n minus 1 constraints. Here's an example. The standard joint typicality that we saw before, when S was equal to 1, 2, we actually had to be singularly typical here, singularly typical here, and this pairwise typical here, in order to be jointly typical for x and y. In this particular case, it's really x1 and x2, where x1 and 2 are the superscript. Any questions about this? Is this clear? This is a generalization of what we've seen. Notationally, we're going to say that the typical set A sub epsilon super n is equal to the typical set with argument v. So all m elements of that vector are being utilized. So this is really like a set function, right? So like this, as a function of the index set of the elements of the vector, we can actually say, oh, well, what is this? Well, this is really just equal to the typical set of the union. Okay, so this is a notation that we saw before. Everyone should be familiar with us with this. I mean, basically, it's saying that an is to the first order of the exponent equal to 2 to the n b plus or minus epsilon. That basically means that this bit is true here. And another way of saying this is that polynomial factors don't matter in this exponential sequence. So any polynomial in n is not essentially going to get canceled out once you take the log. And so what do we mean by typicality in this most general sense? Saying that for all epsilon, for all null negative, for all positive epsilon, there's some point n naught at which for all n greater than n naught, we have that this set has all of the probability according to epsilon. Any particular typical sequence has the same probability, which is 2 to the negative nh. The size of the typical set is equal to 2 to the nh, right? Because if they all have the same probability and that's all of them, then we just take the ratio. That's all of them. That's the count of them. So this is like what we've seen before. And then lastly, if we actually have two sets of elements, S1 and S2, then if these guys are jointly S1, S2 typical, then the conditional probability, the probability of one given the other, is going to all have the same probability. It's going to have probability equal to 2 to the n, the conditional entropy, 2 to the negative n conditional entropy, which is this. So that's not too surprising. In fact, these are easily provable using the stuff we've already done. So there's no point in proving all that stuff. It's just the weak law of large numbers applied again. And it's a straightforward generalization of what we saw for channel capacity. This is another thing that we want to say, that it sort of bounds the size, and it's saying, okay, so this definition here is the typical S1 given S2 sequences, and it's all of these sequences, all of these S1 sequences, such that it's S1, S2 jointly typical. So it's kind of like you're given a typical S2 sequence, and you want to see all of the sequences that are jointly typical with S2, all the S1 sequences that are jointly typical with S2. And so given that definition, then any such typical S2 sequence, which is this guy, and for any such typical S2 sequence, then we can actually have a bound. We have a bound of the typical, of the S1 typical given S2 sequences, which is this size here. And it's just basically equal to 2 to the n, the conditional entropy. So this also should, I think, be fairly obvious to everybody. And then we also have a lower bound on the size. In this particular case, we have, actually, we're taking the expected size on the right-hand side here. Here's the expected size of this typical S1 given S2 set. And it has the lower bound, which has exactly the analogous form to what we saw before. So I don't think we need to prove any of this stuff. It's pretty obvious. One thing that we absolutely need is this one. Because remember before, the way we proved the channel capacity theorem, was we said, what's the probability that two sort of independently, singularly typical sequences would be jointly typical in this sense? So like, for example, if we draw x1 and x2 independently times the probability of x1, probability of x1 times the probability of x2, so that's an independent distribution, how likely is that to be jointly typical? And we saw that that was dependent on the mutual information. And if the mutual information was very, very big, then these two marginally typical sequences were very, very unlikely to be jointly typical. And that's what we have here. That the probability of such pairs being marginally typical but independent of each other, probability of that being jointly typical was 2 to the negative n times the mutual information. And we have a generalization of that notion as well. But in this particular case, we're making it associated with a particular Markov chain. So let's suppose that, for example, S1, S2, and S3 form a Markov chain, which is basically saying that conditioned on S3, X1 and X2 are independent. S1 and S2 are independent. And again, when I'm using the name of the index set to refer to the random variables, I'm just saying that S1 and S2 are independent given S3. What that really means is that the random variables indexed by S1 are independent of the random variables indexed by S2, given the random variables indexed by S3. And so when you have such an independent state, independently drawn random variables, so they're drawn according to this distribution. Right? This is the Markov chain-like distribution for which there's a forced independence. Then what's the probability of them being jointly typical? Well, it's equal to 2 to the negative n times the conditional mutual information of S1 and S2 given S3. Okay, so does everyone see? I think this is important. Let me just pause a minute. Does everyone see how this bit up here is generalized to this bit down there? So like, for example, if we set S3 to be equal to the empty set, then we'd get S1 and S2 being marginally independent. These are drawn independently from the probability of S1 and the probability of S2. Here we're generalizing it a little bit by saying it's conditionally independent. And so we've got, and so the true typical set need not be independent, right? So the true typical set allows them to not be independent. If they are independent, then the probability of them being typical is going to be 1, right? If they are conditionally independent, because the mutual information of S1 and S2 given S3 is going to be 0. But depending on the degree to which they are not conditionally independent corresponds precisely to the degree to which the conditional mutual information is greater than 0. And that's the exponent in how unlikely this event is and how quickly it goes to 0 as n gets big. Yeah.
So why do we want this extra S3 subset of V?
Because when we're doing network information theory, we still want to be able to do these error bounds by saying, okay, well, how likely is it for these sort of independent guys to actually create a jointly typical set which is going to screw up our code? So we want to be able to generalize this to allow other forms of independence.
So S1 is kind of like the transmitters, S2 is kind of like the receivers, and S3 is kind of like the interferers.
You could think of it that way. And this is a very generic theorem. It allows us to. It's applicable in many circumstances. That's a good point. Other questions?
So if all the users are active, isn't it enough just to evaluate the sum rate and find the capacity upper bound for the sum rate only, or we need to take care of like any subset of the users?
The sum rate? No, it's not, because that can actually offer, depending on the setup, that can actually change the achievable region. It's not sufficient to just look at the rate of the sums. because the rate of the sums, there might be singular bounds on the individual rates, which are not captured by the sum rates. I mean, I have a picture of this in a minute. To answer your question, you'll see these kinds of pictures, but like, what you're saying is everything looks like that. That's not true. The rates might look like this. I'll answer that picture better when we look at these sort of pictures of actual real polyhedra. I have a couple today. We'll get into it more on Wednesday. But no, the sum rate is not sufficient to define the achievable region. You'll see why in a minute. Maybe I shouldn't bother with this proof. I think the proof is pretty mundane, to be honest. It's just algebra. I think given what we already know, it's easy. So, but I think the important thing is to really understand the statement of the theorem. Everybody understand the statement of the theorem? If you take a look at it again. Okay, so let's talk about the multiple axis channel. And here, this is one special case of the network information theory for which we're already going to see that the sum of the rates is not, putting a bound on the sum of rates is not sufficient to characterize the achievable region. So we've got multiple senders, one receiver, and the goal is to have the rate of information between these multiple senders and single receiver be as large as possible. Now, in this particular case, in this scenario, the senders can't communicate, they can't cooperate, they can't coordinate, they can't corrupt, they can't do anything. The idea is that each of these senders are at disparate locations somewhere, and just allowing them to communicate amongst each other would be hard. They all want to send, it's kind of like Seattle, San Francisco, and Seattle, San Francisco, and Los Angeles. This is an instance of old age when you forget the word that you just said like 30 milliseconds before you said it. So Seattle, San Francisco, and Los Angeles all want to communicate to New York City. But it's expensive for us to communicate to San Francisco and Seattle. Now that was a joke. That was an actual joke. So it's expensive for us to communicate to San Francisco and Los Angeles. So we just want to somehow communicate to New York City. Now we may interfere with each other. Like when San Francisco and Los Angeles communicate to New York City, they're going to disturb the communications channel. They're going to create a noisier environment for us, but we still somehow want to communicate. And we want to understand the achievable region. What rates can we do? What rate triples, in the case of the scenario I just mentioned, are possible? So here's a scenario. Here's an example with two of them. So, like here's maybe Seattle. We've got message W1. Here's San Francisco. We do some coding. It gets into some joint channel. P of y given x1 and x2. What comes out with y, and what the goal of New York City is to sort of decode, well, what did Seattle want to say and what did San Francisco want to say? So we have separate messages, but it's the same physical channel, because what San Francisco does is going to interfere with what we do. This probability distribution allows that. If x2 is something, it might it might restrict. Conditioning on a particular x2, the channel between x1 and y might be very, very noisy, or might be very, very clear. We don't know. And like I said, x1 and x2 can't cooperate. So here's, I think, what will begin to answer your question. So if there was cooperation between San Francisco and Seattle, this would be the rate that we could communicate. Right? It's just, well, x1 and x2 is just a joint random variable. There's a probability distribution over x1 and x2. It's not independent. We just use the standard point-to-point communications scenario. Right? But we want to also assume that this is true. x1 is independent of x2, which basically changes things. And like I said, there's noise between these guys. I've already said all this stuff. Senders can't communicate. I've already said this stuff. So we want to know the relationship between the mutual information and R1 and R2, and also a coding and a decoding algorithm, so that the two senders can still communicate without needing to communicate with each other. And so a good example of this is the discrete memoryless multi-axis channel, discrete memoryless MAC. where we've got x1, an alphabet for x1, an alphabet for x2, an alphabet for y, and a joint conditional distribution for the channel. And we've got a code. I'm running out of time here. I was hoping to answer your question. So it's a sequence of codes where we have two rates now, R1 and R2, right? And depending on the block length, it basically corresponds to the number of messages that we can specify. Like, it depends on the rate. So we'd have, and it's the same block, so things are synchronized. But we have a block of length n, and Seattle, let's say that Seattle is R1, and so we can communicate 2 to the n R1 messages at most, and 2 to the n R messages from San Francisco to New York. And so we've got these mappings, these encoders, that go from message indices to sequences of code words, or to code words, to sequences of source symbols. And then a decoding function. So what New York needs to do, New York needs to essentially take what it received and come back with 2 integers, the Seattle message and the San Francisco message. And it's sufficient to assume that there's uniform distribution. We're running out of time, so we're going to have to start this on Wednesday. So I'll see you on Wednesday. See you later.